DesignLinx was founded in 2009. We've been in business 10 years. We are a veteran-owned small business, and we're experts in providing Xilinx solutions. We focus inside the pins, as we say in the FPGA world, as a premier partner for Xilinx. The markets that we focus on: aerospace and defense, video image processing, medical, and industrial, just to name a few that we've played in. Trilogic has been a great partner for us as well, and vice versa. We've been an advanced technology partner since 2010, as Molly said, providing design, simulation, and advanced verification solutions. Some of our service offerings, certainly FPGA design, we support full and partial projects. And one thing that we feel differentiates us from other firms is our verification methodology. We support Verilog, System Verilog, and UVM and UVMF, as you'll learn today. And LVO acceleration support and deployment services as well for machine learning and acceleration, and embedded processing solutions for anything Xilinx. So supporting Linux, RTOS, bare metal, middleware, C, C++, etc. So our contact information is right there on the lower left side. You can reach us through our website or just email info@designlinxhs.com, and or certainly just use the phone number there, and that'll reach us in the sales department. That's what he had. Thanks, George.
You're all set. All right. Thanks, Molly and Don, for the intro. As you see, this is a practical encounter with UVMF. So this is a real live thing that I personally went through with UVMF, and I'm going to show you some about it. I'll go through a small introduction and then talk about UVMF DVE structures and benefits, where to get training for UVMF, and then the meat of this webinar, create a UVM compliant DV from scratch. So to demonstrate that, I'll talk about first the UVMF code generator and what it actually creates for you, and how you can customize the top test control of a particular example that Mentor Graphics puts out called the ALU. So let's get right to it. As a background, as I said, practical first-time experience with the UVMF. The purpose of this is to show you UVM from scratch, the template generation, and customization. And as I said, we'll be talking and demonstrating an actual example design. This webinar is actually based on a Trilogic white paper that I authored earlier this spring entitled UVMF Beyond the ALU Generator Tutorial, Extending Actual Test Control of the DUT Inputs. You see the graphic on the right there, and that should be available through Trilogic, and I think Molly can talk to that at the end and provide a link. The benefits of UVM. No required UVM template. In my experience with UVM projects, I've always had a template to start with. Well, what happens if you don't? Mentor Graphics has UVMF, which is kind of advertised as UVMF testbench generation in an hour. Well, that's not quite the whole story. There's quite a bit more left to do for the verification engineer. So the tools that he has to do this starts with the UVM code generator, which is a script-driven mechanism, either in Python or YAML scripting, and it creates the whole framework for you, perhaps in an hour, but what do you end up with? Well, lots of code just to start with. So UVMF is really a jump start on UVM. The output is factory created framework. It's all UVM compliant coding. Out of the gate, there's no coding errors. It compiles and runs the first time. It also embodies RVM reuse and provides a standard methodology for you to evolve the the DVE, and allows the engineer to focus on creating customized functionality. But how do we do that? That's the basis of this webinar. Also, as an added thing, UVMF can also be configured to target Veloci emulation. And that's a whole another subject. I won't be talking about that today. The UVMF structure ends up being its own inherent architectural structure. As this Mentor Graphics pyramid graphic shows, if you kind of abstract this pyramid to the raw materials, starting with raw materials and ending up with a complete home, what happens in between? Well, the basis of UVMF is system Verilog. Then via common verification building blocks, the building supplies are the UVM IP. So beyond that, the UVM use model and reuse methodology is afforded through the UVM framework and the coding of such. So eventually you get completed rooms that are interfaces and environments and packages and so forth. And finally you have a test bench that has that specific bench and a stimulus. The directory structure is very recognizable through any code generation. It's basically two areas. We have a project bench area and a verification IP area. So under project benches, you get the stuff you need to do test writing, a place to add documentation, top level control, project parameters, and the top dot and test bench instantiation. In the other area is the verification IP, which includes the actual framework of interfaces and BFMs and monitors, drivers, and such. And tucked under that is the way you configure the environment, especially that's important for reuse, right? You get configuration there, predictors and coverage and so forth. So where do we get training for UVM or UVMF? The one-stop shop is Verification Academy. It requires a personal membership, but it has a plethora of verification training on not only traditional UVM, but on UVM framework. And there's a 16 video presentation called One Bit at a Time. It's UVMF centric, and it really goes through the whole thing. Intro, connecting transactions, all the way to how to connect a predictor and use it to the scoreboard. The example designs that Mentor Graphics provides to us are in your install. Examples, UVM Framework, UVMF with some kind of version tagged on the end. Today we will be looking at the 3.6G or greater. That's required for some of the scripting methodologies. But you have an array of different example designs you can pick from that have different protocols like AHB or Wishbone has a GPIO example. Today we'll be using actually the ALU example. Particular to UVMF and code generation is another example that interestingly is located in the installed directory but under docs. So it's called Generator Tutorial. There's a presentation that you see this graphic to the left called UVM Framework Step by Step. It's a guide, it's a PDF. And what we're doing today is kind of extending information on top of that guide. So we're going to be using the ALU example, and you can see over to the right, it's a pretty simple dot, has two operand inputs, an operator input and a result. So we'll be working on the A and B inputs. So what's the scenario here? So quote, here is a DUT specification. We have no UVM environment for you to start with as a template, so go and find out how to generate one with Mentor's UVM Framework, UVMF, template generation methodology. So what do you do now? Even if you have UVM experience, UVMF is not standard UVM, although it's compliant. So still a good idea to take some of the training that MGC offers and specifically study the ALU step-by-step guide and simulate the generator tutorial as it is, just to get familiar with it. So how do we begin our creation of a UVMF environment from scratch? The UVMF code generator, as I said, either in Python or YAML script. I'll be demonstrating Python. I believe YAML was a later revision than 3.6G, so that's why I'm there. This is the thing that creates your UVM architecture, and a good reference is the UVM Framework code generator, API reference. So as the graphic shows here, you script a configuration file, and you'll see some of the constructs that will allow you to create the framework and define it. This next slide shows a little bit more in depth of the types of things you would see in a configuration file. But first, there are 4 different areas that you would deal with for creating these constructs, and they would relate to the bench area, the environment area, an in interface, and an out interface. So if we take a look here, we can see that somebody has created an interface called INTF dot, and after the dot you can add ports, you can add type defs, you add transaction variables that you can declare as true, as random, or to be compared automatically. The bench area allows you to add BFMs. So in this case, in this line, ben.add BFM, we are adding actually a driver because the keyword active is part of that construct. If it was passive, it would be a monitor. So then you can create things like agents, which include driver and monitor BFM pairs. You can add clocks, resets. You can add what's called an analysis component, which is actually a port out of the agent to allow you to connect automatically to a predictor of some sort. In this case, we have it named ALU predictor. You can add scoreboards of different types of in order, out of order scoreboards. And then once you get all of this created, you use connections between all of your UVM components to hook everything up. So as I said, you can have one or multiple configuration files, but it's really rather straightforward. There's no UVM experience required to actually create a test bench here, but as you can imagine, it requires a pretty solid DUT and DVE spec to get it right the first time. So this is kind of a graphic of what you end up with out of the code generator. Test control, unfortunately, that's not shown, but I will show a graphic of that a little bit later. You get your top DUT, you get all the nice interfaces, transaction sequences, drivers, predictors, scoreboards. Boom, you got them right away. Generation here is one and done. Right, because the use mode for this is you would take the output of this and copy it to your working area and then start working on it. So if you were to create another one, you would not want to overwrite any of your customizations. But rerunning of the code generated is quite useful by example. If you say you need to add an agent or an interface or a transaction variable, you can go back to your code generation area, rerun it, and then take a look at it and see how it changed the environment and manually transpose it. So, but the really cool thing here is that it compiles and it runs. Next, we have to customize the output. So if I iterate a quote here from the UVM Framework User's Guide, the Python scripts provided automates the creation of the files, infrastructure, and interconnect for interface packages, environment packages, and project benches. Once generated, developers can promptly focus on adding functionality specific to the design and interfaces used. So, boom, in short order, you have hundreds of files, thousands of code lines with a large directory structure, all connected, compiles, runs, goes into Questa. You can post waveforms, but it does nothing. So what do you do now? Your UVMF template is lacking functionality. Your generated tests have no concept of the DVE functional spec. Your sequences, transactions, drivers, monitors, agents have no synchronization. Your predictors have no idea what or how to check results. So you need to customize your new DVE. By demonstration, I'll show you how to have a solution for one of those issues, and that's top test control. So what we're going to do is take the operand A and B input, and we're going to extend it to the top level test area so that you can manually tickle those bits. The reason why we're not able to do that initially out of the code generator is because as I said, it doesn't know how to do that. It doesn't know that you actually want to manually stimulate it. Plus, in this particular example, the A and B inputs are randomized further downstream just to the input of the ALU driver input. So I'll show you how to extend manual stimulus control to the top tests. And in doing that, we'll be adding and extending new sequences so that you have a path directly from top to the ALU in driver. It'll be a practical implementation step by step, leaving out the operator that's left as randomized. And this solution was fully implemented and verified in a simulation. Further, if you're interested in actually seeing or having the files, they are available through Trilogic. So here we go. Here's the graphic of the extending top test control. From the top, in the green box, we have our new ALU manual test. In the bottom, we have the ALU in driver agent, which feeds the pins of the dot. So how do we get there? We create a new test that has the A and B logic to be able to tickle it at the top. It'll feed the ALU manual sequence, which is an extended bench sequence. That gets you to the boundaries of the bench area, which I explained before. Then you need another transaction to actually get it to the driver, which is in the verification IP section. So we're going to extend a bench test and 2 bench sequences in our process of customizing the front end. And it's really quite simple. To extend the top bench test, you can simply copy the ALU random test.svh file, which in itself extends the test top, which you can see in the graphic to the right here. So if I'm copying this guy that has that guy, I am extending the ALU manual test from actual test top. So you get all the benefits of of what the base test is. Next, just change the text in there from random to manual. Then you have to create a manual sequence which allows you to override the ALU bench sequence base that exists already in that test. So by virtue of changing random to manual, you would get ALU manual sequence. So that's satisfied. The next thing is a little bit more abstracted. The test comes with no task body. That's because it doesn't do any manipulation of the inputs from the top level as it was randomized downstream. So you can copy from any UVMF example test that has a run phase, and you can edit that by, so here's a run phase, test run phase that just goes at the bottom of your body of the test, and you just rename it appropriately, create the sequence, initialize the A and B inputs, and then add a repeat section that simply repeats, that controls the sim length. And here's your actual manipulation of the inputs. And with a start, you'll do 100 loops here, and you'll be stimulating an incrementing pattern to the A and B operand inputs. So likewise, we have to extend two sequences. The first one is the bench. In the same fashion, copy ALU random sequence.svh to ALU manual sequence.svh, change random to manual, add the logic assignments or logic declarations for the sequence variables, and then assign ALU and A and B inputs so that it passes it on to the next sequence in line, which is the ALU in agent manual sequence. One more to go. So to get to the driver BFM, you have to get it from the above sequence to the body through an ALU in manual sequence. Copy that random sequence to the manual sequence, do the same changes, same declarations, create the assigned logic assignments that actually pass the data on to the operands in the dot, and then this section, since you've created a new ALU bench sequence base, it's required that you add the manual sequence to the ALU bench sequence base.svh file. So this in short term allows upstream bench sequences to utilize what you've created below it. So it's just another handle using the typedef construct. There's one final step. Any new files are required to be added to the package files that are in each section of our environment. In the bench section, we have a test package. Also in the bench area, we have a sequence package that the ALU manual sequence has to be added to. And then finally, in the verification IP area, ALU in package has to have the ALU in manual sequence. This is just a simple include file. So to be able to run the test, there's one small area that you have to change, and that's just the UVMF home. We need to point to the UVMF 3.6G revision of the tools, so that anything prior to that, I don't know that the scripting works, but I was required to do that. Change the test name to your new ALU manual test, and then run the simulation with the standard make targets for running Questa with or without the GUI. So you've done all your edits. You have top test control working. In conclusion, UVM proficiency is a very steep learning curve. It usually requires many years of experience to be able to architect UVM DVE. It really helps to have system Verilog background and inherent good test bench philosophy, design philosophy. But in the end, UVMF offers reasonable, manageable opportunity to architect UVM with little to no UVM experience. So this front-end customization presented here can actually be directly applied to completing other noted customization areas. The enablers for this are the training and the examples. And I can't emphasize this more, is being able to simulate something that is not quite working, to be able to insert code and setting breakpoints and just experimenting with and learning how your UVM template works. Again, all the modified and new ALU design files are available via Trilogic. In closing, UVMF can get you 80% there, well, maybe the code base anyways, and from there it is truly within the grasp of the verification engineer to create a customized and useful UVMF environment. Go UVMF. So that concludes my presentation. Thank you.